Imagine a power plant that runs on seawater, produces zero carbon emissions, creates almost no long-lived radioactive waste, and can't melt down. This power source is so abundant, it could run civilization for millions of years. For 70 years, people have called fusion 30 years away. But in 2025, something has fundamentally changed. We're not just chasing science anymore, we're building actual power plants. Private companies have raised more than $10 billion. And Google and Eni just signed billion-dollar power purchase deals. The first commercial fusion reactors are targeting the early 2030s. So is the dream finally becoming reality? Or is this just the biggest hype cycle yet? Stick around, because today we're separating the breakthroughs from the bullshit. Hey everyone, welcome back to Eduverse. If you're new here, hit subscribe real quick, because we dive deep into energy, tech, and the future. Today we're talking nuclear fusion, the holy grail of clean energy. I just read a monster 5,500 word report on where fusion actually stands in late 2025. And I'm turning the key takeaways into a fast, honest script so you don't have to. Let's go. First, the big picture. The world is facing an energy trilemma. Electricity demand is exploding thanks to AI data centers. We have to decarbonize yesterday. Solar and wind are amazing, but intermittent. Fusion solves all three at once. Fuel from seawater and lithium. No CO2, virtually no long-lived waste, and no meltdown risk. The reaction stops if anything goes wrong. And it offers insane energy density. 1 spoonful of fusion fuel equals 1 barrel of oil. It's literally the same reaction that powers the sun. The only question is, can we make more energy than we put in? And do it cheaply enough to matter? This is the part everyone messes up, so listen close. There are different kinds of Q in fusion, and they mean totally different things. Q plasma, or scientific Q, is fusion power out divided by heating power in. When this hits one, you've got scientific break-even. Q engineering, the one that actually matters, is total electricity out divided by total electricity the whole plant consumes. For a real power plant, you need Q engineering of 25 to 40. We are nowhere close to that yet. In 2022, the National Ignition Facility, or NIF, announced ignition. They got 3.15 megajoules of fusion energy from 2 megajoules of laser light hitting the target. Sounds like net gain, right? Wrong. The lasers consumed approximately 400 megajoules of wall plug electricity to make those 2 megajoules of light. By April 2025, they pushed target gain to 4.13 times, which is incredible science, but still hundreds of times away from a power plant. Moral of the story: celebrate the physics wins, but don't confuse lab ignition with free electricity. The global race to achieve commercial nuclear fusion is intensifying, promising a clean, abundant, and virtually limitless energy source. Unlike nuclear fission, fusion produces minimal radioactive waste and carries no risk of meltdown, making it a highly sought-after energy solution. Let's explore the key players and technologies driving this global effort, starting with the mega international tokamak, ITER, in France. Involving 33 countries, ITER aims to demonstrate fusion feasibility on a power plant scale, with first plasma expected in 2025 and deuterium-tritium operations by 2039. While slow and over budget, ITER is crucial for testing full-scale breeding blankets and diverters, essential components for future fusion plants. Commonwealth Fusion Systems, or CFS, a private company from MIT, is developing smaller, cheaper tokamaks using high-temperature superconducting magnets. CFS plans for its Spark demo to achieve net plasma energy gain by late 2026, with its ARC commercial plant operational in Virginia by the early 2030s. They've already secured significant power purchase agreements, including a 200 megawatt deal with Google, demonstrating real commercial traction. Stellarators, like Germany's Wendelstein 7X, are also making strides, setting world records for plasma performance. Startups like Proxima Fusion and Type 1 Energy are exploring this technology, which offers the advantage of natural steady-state operation. China is also a major player, with its East Tokamak achieving a record 1,066 seconds of high confinement plasma in January 2025. Their new best tokamak, finishing in 2027, aims for burning plasma and significant fusion power output. While inertial confinement fusion, like NGEF-C, continues to improve, building a power plant with this technology presents unique engineering challenges. However, the engineering aspects remain the brutal part, posing significant hurdles to commercialization. One major challenge is materials science. Reactor walls must withstand extreme temperatures and neutron bombardment for years. Currently, no qualified materials exist that can last a commercial lifetime under these harsh conditions. Another hurdle is tritium breeding. A single large plant needs tons of this scarce fuel, which must be bred from lithium inside the reactor. Plasma disruptions, sudden terminations that dump gigajoules of heat, also require reliable control systems, with AI controllers offering promising solutions. Finally, cost is critical. Capital costs must drop significantly to make fusion competitive with other baseload power sources. A realistic timeline suggests the first small commercial plants could be online in the early 2030s, with gigawatt-scale plants by the late 2030s. By 2050, fusion could supply 10 to 50% of global electricity, depending on how quickly costs fall. Analysts predict a $40 to $80 billion industry by 2036 if key milestones are met, indicating a massive market potential. So, is fusion still always 30 years away? No, the physics door is open, and we are now in the brutal engineering and commercialization phase. The race is real, with billions on the table and nation-states and trillion-dollar tech companies fully invested. We might be one materials breakthrough or one lucky demo away from the biggest energy revolution in human history. If you want to follow this story as it unfolds, hit that subscribe button and ring the bell, because the next 5 years are going to be insane.